Welcome to Unit 2 of our course. This is where we start to drill down on that TCP/IP model that we've been talking about recently. This course is based on the text by Jim Couros and Keith Ross entitled Computer Networking, a Top-Down Approach. So let's get started. Internet applications include the classic text-based applications that became popular in the 1970s and 1980s. Text email, remote access to computers, file transfers, and news groups. The one we may be most familiar with is the World Wide Web, encompassing web surfing, search, and electronic commerce. They include instant messaging and peer-to-peer file sharing, the two killer applications introduced at the end of the millennium. Since 2000, we have seen an explosion of popular voice and video applications, including voice over IP and video conferencing over IP, such as Skype, user-generated video distribution, such as YouTube, and movies on demand, such as Netflix. During the same period, we have also seen the emergence of highly engaging multiplayer online games, including Second Life, Mass Effect, World of Warcraft, and many others. And most recently, we have seen the emergence of a new generation of social networking applications such as Facebook and Twitter, which have created engaging human networks on top of the Internet's network of routers and communication links. Clearly, there has been no slowing down of new and exciting Internet applications. In this unit, we studied the conceptual and implementation aspects of network applications. We began by defining key application layer concepts, including network services required by applications, clients and servers, processes, and transport layer interfaces. We will examine several network applications in detail, including the web, email, DNS, and peer-to-peer file distribution. We will then cover network application development over TCP and UDP. In particular, we study the Socket API, Application Programming Interface, and walk through some simple client-server applications in Python. At the core of network application development is writing programs that run on different end systems and communicate with each other over the network. For example, in the web application, there are two distinct programs that communicate with each other. The browser program running in the user's host, which is his desktop or laptop or smartphone, and the web server program running on the web server host. As another example, in a peer-to-peer file sharing system, there is a program in each host that participates in the file sharing community. Thus, when developing your new application, you need to write software that will run on multiple end systems. This software could be written, for example, in C, Java, or Python. Importantly, you do not need to write software that runs on the network core devices, such as routers or link layer switches. Network core devices do not function at the application layer, but instead function at the lower layers, specifically the network layer and below. This basic design confines the application software to the end systems. From the application developer's perspective, the network architecture is fixed and provides a specific set of services to applications. The application architecture, on the other hand, is designed by the application developer and dictates how the application is structured over the various end systems. In choosing the network architecture, an application developer will use one of the two predominant architectural paradigms used in modern network applications, the client-server or the peer-to-peer architecture. In client-server architecture, there is a 24/7 host called the server, which services requests from many other hosts called clients. A classic example is the web application for which the web server services requests from browsers running on client hosts. When a web server receives a request for an object from a client host, it responds by sending the requested object to the client host. Note that with the client-server architecture, clients do not directly communicate with each other. For example, in the web applications, two browsers do not directly communicate. Another example of the client-server architecture is that the server has a fixed, well-known address called an IP address, as you recall. Because the server has a fixed, well-known address, and because the server is always on, the client can always contact the server by sending a packet to the server's IP address. Some of the better-known applications with client-server architecture include the web, FTP, telnet, email, and today banking has become a major application for the client-server architecture. Often in a client-server application, a single server host is incapable of keeping up with all the requests from clients. For example, a popular social networking site can become quickly overwhelmed if it only has one server handling all requests. For this reason, a data center housing many hosts is often used to create a powerful virtual server. The most popular internet services, such as search engines like Google and Bing, internet commerce, Amazon and eBay, web-based email like Gmail and Yahoo Mail, social networking, Facebook and Twitter, employ one or more data centers. As mentioned in the last unit, Google has 30 to 50 data centers distributed around the world, which collectively handle search, YouTube, Gmail, and other services. In peer-to-peer architecture, there is little or no reliance on dedicated servers in data centers. Instead, the application exploits direct communication between pairs of intermittently connected hosts called peers. The peers are not owned by the service provider, but are instead desktops or laptops just like yours, controlled by users, with most of the peers residing in homes, universities, and offices. Because the peers communicate without passing through a dedicated server, the architecture is called peer-to-peer. Many of today's most popular traffic-intensive applications are based on peer-to-peer architectures. These applications include file sharing like the BitTorrent application, peer-assisted download acceleration, internet telephony like Skype, and IPTVs such as CanCan and PPStream. One of the most compelling features of peer-to-peer architecture is their self-scalability. For example, in peer-to-peer file sharing application, although each peer generates workload by requesting files, each peer also adds service capacity to the system by distributing files to other users, to other peers. The peer-to-peer architectures are also cost-effective, since they normally don't require significant server infrastructure and server bandwidth. Peer-to-peer applications face three major challenges. Most residential ISPs, including DSL and cable ISPs, have been dimensioned for asymmetrical bandwidth usage, that is, for much more downstream than upstream traffic. But peer-to-peer video streaming and file distribution applications shift upstream traffic from servers to residential ISPs, thereby putting significant stress on the ISPs. Future peer-to-peer applications need to be designed so that they are friendly to ISPs. Because of their highly distributed and open nature, peer-to-peer applications can be a challenge to secure. And thirdly, the success of future peer-to-peer applications also depend on convincing users to volunteer bandwidth, storage, and computation resources to the applications. Well, I think this is a pretty good spot to stop on this lesson. Go ahead and take care of whatever assignments you have on this particular lesson, and when you are prepared to start again, come on back and we'll continue.